Today we're going to continue with volumes using discs and washers. This is part 2. So today we're going to be rotating about the y-axis, which is going to mean that our cross sections are now perpendicular to the y-axis, and that's going to change how we calculate our radius. Last day we looked at rotating around the x-axis, and our cross sections were perpendicular to the x-axis. We remember this means that the thickness of each disc or washer was delta x. Today, if we rotate around the y-axis, we would have a disc or a washer that now has a thickness of delta y. This means that we are going to be integrating with respect to y. This means that our upper and lower bounds are now y values, and our area is still what we are integrating. However, our area now is going to be with respect to y. The area of each of these now is still pi r squared, but our radius now is going to be a function with respect to y. So if I think of this one on the left here, this is the function y equals x cubed. But if I look at the radius of this, the radius of this is an x value. Well, the x value at that point would be the cubed root of y. Okay. So when we are rotating perpendicular to the y-axis, our cross sections are perpendicular to the y-axis, our bounds should now be y values. Okay. We now have a radius, which is going to be f of y, and we're going to integrate with respect to y. Okay? So if we are perpendicular to the x-axis, we should have bounds that are y values. Our radius is f of y, and we need to integrate with respect to y. So we should have a dy. And that's because our thickness now of each section or each slab is delta y. If we rotate about the x-axis, we would be perpendicular to the x-axis. We integrate with respect to x, so we have a dx. Our radius is f of x, and our bounds are x values. So in this case, our volume is going to be two values c to d. So in this case, your c is now your lower end, and your d is now your upper end. Our area is now with respect to y, and we integrate with respect to y. So our area is still things like pi r squared. There's still a circular slab or a washer where you'd have pi big R squared minus pi little r squared. But now our function should be in terms of y, or in other words, x equals. Okay. So let's try one here. Again, we're going to draw the area, draw the volume. This time we're rotating about the y-axis, so we're going to be rotating this way. Okay. We have y equals x squared. Okay. We have y equals 9. And we have x equals 0. So our area here that we're rotating would be this area. Okay. So when we rotate this, about our y-axis, it's going to rotate to create a circle. It's going to kind of be like a pine cone shape a little bit. And each slab would look like this, be a circular disc. And our radius here of each circular disc is going to be f of y. Well, in this case, we have y equals x squared. So this is not f of y, this is f of x. So we need to rewrite this. This would be plus or minus y equals x. Since we are only taking that positive portion, we're going to have root y equals x. This is our radius. Our area of each disk is always pi r squared. So in this case, pi times root y squared, or pi y. Because we are rotating about the y-axis, our upper and lower bounds should be y values. So we need the y coordinates of the intersection. We need this point here and this point here to be our upper and lower bounds. So this would be 0, and this one here is 9. We're rotating about the y-axis, so we need the y coordinates of intersections because we're taking the function with respect to y. So we can proceed. Therefore, our volume is going to be the integral from 0 to 9 of the area, which is pi y, integrated with respect to y. So if we think about this, this was adding up. This time we're adding up slabs vertically. The slabs have thickness delta y, which means we're integrating with respect to y. That's where the dy comes from. And each slab has an area of pi y. So we're integrating or adding up an infinite number of slabs from y equals 0 to y equals 9, vertically piling these up on top of each other, adding up all those areas. The areas are pi y. Okay, so that means our volume is going to be pi times 1/2 y squared, evaluated from 0 to 9, or we get 81 pi over 2. Again, note for a vertical axis of revolution, we're integrating with respect to y. Our slabs are perpendicular to the y-axis. Let's try one more. This time we have y equals x squared. We have x equals 2. And we have y equals 0. The area that is enclosed by all three of these would be this area in here. Okay. So when we rotate that area, this is our area that we've got. We're rotating about the y-axis. So it's going to rotate over here. And therefore, our slabs are going to be circular discs. Okay. So it's going to sort of make, it almost looks like a cup or a glass where the bottom is thicker than the top, so it kind of tapers up towards the top there. Okay. So each of our circular discs, the question is, what is our inner radius, little r, and what is our outer radius, big R? So our outer radius here, remember this is with respect to y, right? So this should be an x equals function. Well, this was x equals 2. Our inner radius, little r, goes towards the actual function that we drew. So that function was y equals x squared, and our inner radius, little r, should be in terms of x equals as well, right? Because we're integrating with respect to y. So if we have y equals x squared, this is the same thing as x equals plus or minus root y, but I'm only taking this positive arm. So we just get x equals root y. So our inner radius is root y. Okay. We need our bounds. So our bounds are y values. So we're starting at y is 0. The question is, where are we ending? Well, we're ending right here, where our purple line and our blue line meet. So our intersection is when root y equals 2 or y equals 4. Okay, so blue line, purple line, where do they meet? They meet when y is 4. And then we are taking pi big R squared minus pi little r squared, and we're integrating with respect to y. Okay. So that's going to give us pi. I can take that out. Big R squared is 4. Little r squared is y. And we're integrating with respect to y. So we can find our areas separately and then plug them into our formula. So we could have said, okay, our area is pi big R squared minus pi little r squared, which is going to give us pi times 2 squared minus pi times root y squared, which gives us 4 pi minus pi y, and done it that way. But we can also just go straight to the integration. Okay, factor that pi out, big R squared minus little r squared. This gives us pi times 4y minus 1/2 y squared, evaluated from 0 to 4, which gives us pi 16 minus 2 minus 0, sorry, minus 8. 16 minus 8, again minus 0, which gives us 8 pi. And that's it.